Now the question, of course, is what happens in the second part of the exam guideline? Remember, I said we have 3 parts. But let's look at my screen quickly because I want to remind you about something. Let's look at it. 1. Do not learn definitions that are not in the exam guidelines. They may not be accepted. Does everybody hear that? Did everybody hear that? You must not, at any rate, learn definitions that are not in the exam guideline because you never know, they might not be accepted. Then, secondly, the examiner guidelines inform you what is expected of you. It informs you what is expected of you. So I would suggest that you really get into it and use the exam guideline to the maximum. Here's the second part on page 20. But before I go there, let me first say 1 or 2 other things. If you aren't convinced now, you don't have an exam guideline, make a plan today. Like a note to your teacher there, please get us an exam guideline. Teachers, I'm putting pressure on you, but I think the learners would be well prepared if they actually work through the exam guidelines. Let's get back to page 20 of the exam guidelines. Let's look at part 2. Part 2 says in the exam guidelines, part 2 is about equilibrium constant. And it says the following: list the factors that influence the value of the equilibrium constant, Casey. And I can give you that answer now already. It is temperature. So the one factor that influences Casey, now you may not know what Casey is, but I'll explain that for you in a minute. Then they say, write down an expression for the equilibrium constant. If you are given an equation for the reaction, I'm going to show you just after this how to do that. Then they say perform calculations. I'm going to do that with you also now and give you significance of high and low. I will just refer to that because they didn't ask that last year. Okay, so the question is, what are they going to ask me from here? I can tell you already they're going to ask you that one, and that one in the exams. They've done so last year. They must ask you Casey in the exam. They must ask you to write the expression. They must ask you to do calculations. They might ask you to do the significance of high and low. And number 1, that one is important because the only factor that influences Casey is temperature. Does everybody hear that? The only factor that influences temperature is that influences the equilibrium constant is temperature. Right, everybody, are you now ready for the next part of the question? Remember what my aim is today? I want to take the exam guideline, list the factors that has an effect on Casey, write an expression when you are given the equation, then do calculations on it, and then say why, if the answer is big or small, what that means. I'm going to explain to you what it means. Right, let's go and tackle this problem. Question 5.2 starts off like this. The reaction mixture is analyzed at regular time intervals. The results obtained are shown in the table below, and then they give you this table. So let's analyze the table. Time, seconds, 0, 2, 4, 6, 8, 10 seconds. So at 0 at the start they measured, then after 2 seconds, so every 2 seconds they were measuring what was the concentration of X2 and what was the concentration of X3. You got that? So at the beginning, at time 0, there was 0.4 of X2. Then it started dropping because this is the X2 is the reactant. The concentration must drop. Why? To become more on that side. So this drops, that becomes more. So that number must increase. It's increasing? Yes, it's increasing. This must drop. The concentration must drop. 0.4, 0.22, 0.08, 0.6, 0.60. Hey, it's starting to become constant now. The concentration is becoming constant. Let's look at this one. At the beginning, there was no product, and then it was 0.1, 0.2, 0.226, 0.2. Hey, it's also becoming constant now. Right. Now, next point. I'm going to put this on a graph just to show you the same thing again. So I drew this graph and I said, right, this is X2, that one there, and the concentration is dropping. Concentration is dropping. And this is the purple graph, is the product X3, and that's increasing from 0 to 0,226. 0,226, 0,226, 0,226. And the product's concentration was decreasing from what? From 0,4. It decreased because it was used up to make the products, reactants, and the reactants came down and became 0,206, 0,06, 0,06. So can you see here something strange going on here? That it looks like the reactants reach a point where they become constant, 0,06, 0,06, and the products increase until it became constant, 0,226, 0,226. Got that? So what can we say? What is the state of affairs during a chemical reaction where the concentrations become constant? What is that? If reaction is at equilibrium, the concentration of each reactant and the concentration of each product, concentration of X3 will remain constant. Reactants remain constant. Products remain constant. That is a principle that you need to know. You got that, everybody? Let me talk to you again. You need to make sure that you get that one. If the forward reaction, that's right, if the forward reaction equals the reverse reaction, then there comes a stage where it gets constant. But we can't see that movement, but the molecules do that. That's right. They become 0,06 and 0,226. Okay. Now, what do we do with those constant numbers? And this is where, Casey, the constant number comes in. Let's look at this. Let me just finish this off. So 2 points you have to remember. 1, the concentration of X2 and the concentration of X3 is constant at equilibrium. You got that? It's constant at equilibrium. And 2, we find that it does not mean that the concentration of X2 is equal to the concentration of X3. Let me explain that. It does not mean that this must also be 0,026. Now this has its own concentration which is constant. This has its own concentration which is constant on its own, not according to those numbers. So that's why we say the two of them are not equal to one another. So this isn't 0,06 and that's 0,06. If you get the point what I'm trying to say. Okay, we got that 1 point. The concentrations of reactants on its own remain constant. The concentration of the products remain own. But the two of them have their own concentration mole per decimeter cube. The two are not the same. The rates are the same, but the two are constant. You got that? Make sure you understand that very clearly, because we must apply that. Now we must do the calculation, because here comes the question of 5.2. Notice, they said earlier on, you need to be able to write an expression for Kc if you are given the equation. Have you seen the equation? Let's talk about it again. Here's the equation. Now we need to get the expression. There's the table again. The question says, calculate the equilibrium constant. Mind you, the concentration is constant for the products. The concentration for the reactants are constant. Look at that line. You know from the maths, You know from the maths? That's a constant one, no turning point there. That's right. So equilibrium started there where the lines. Equilibrium did not start there. There's not equal there. The concentrations are equal, but this is the equilibrium start when the lines are parallel. Everybody understand that part? Now, here's the question. They say calculate the equilibrium constant Kc. Now let me just say two things about Kc. K is a constant, meaning a number in which we use concentrations. In other words, we use those concentrations and those concentrations. Concentrations of the reactants, concentrations of the products. That is what we're going to use. So we use concentrations and we work out a number. And this is how we do it, and I'm going to explain this to you after this. So we write Kc, that is the constant, where we're going to use these numbers now during equilibrium, is equal to the product X3 squared. Product X3 squared. Compared to, divided by, the reactant X2 cubed. The reactant X2 cubed. Wow. Interesting, huh? And then I take that value of X3. Where is X3 now? X3 is 0.26, X3 is 0.26. And I put that value down in round brackets because that is the expression, that's chemistry. This is mathematics, round brackets, 0.226. Square it. 0.226 square it. Then take 0.06 cube it. And I get that answer on my calculator. I hope that you're doing it there as well. I hope that you're doing it there as well. Where you are, did you see that what I did? Do you see what I did? I divided the one by the other, the products by the reactants. Then I get a comparison, a ratio. I can see is there a lot of products compared to the reactants that I put in. That's really what's going on. But I square it, I take the coefficients, I put it, I make it as a what? A power, that's right, or an index. I will explain it now slowly again, how we write an expression, because that's important for you to see.